Hello everyone, this is Yash Patel of Team Mamba Mentality. We present to you the Spacecraft Lighting Network System. This is a design challenge by the Texas Space Grant Consortium with the topic offered by NASA. Here's our team. From left to right are Mehdi, Eduardo, Yash, myself, and Omar. We are seniors at the University of Houston majoring in electrical engineering. Our mentor is George Salazar, who's an engineer at NASA, and our faculty advisor is Dr. Robert Prones, who's also an engineer at NASA and an instructor at the University of Houston.
The spacecraft lighting network system includes three key concepts that are crucial to understanding the purpose behind design choices and future goal implementation that will be obtained in the fall semester. The first concept will be demand for updated system infrastructure. NASA's current lighting network is based on manual toggle switches, and many commercial lighting controllers are unable to function in radiation-heavy environments. FPGAs have made large strides in this field, and a focus of this project is implementing DMX protocol into an FPGA board. The second concept will be the DMX protocol. This is an addressing system that allows a user to control multiple lighting fixtures within a network. The third concept will be the spacecraft lighting network system, which will compose of two Arduinos that communicate via Ethernet port. Their relationship with the FPGA will be explained in further detail later in the presentation. In order to ensure our project's completion, we must make sure to follow these objectives. The first one being implementing DMX protocol into a programmable device, our choice being the FPGA board. The second one being communicating via Ethernet. This will be done between two Arduinos in our SLNS portion of the project. The third will be light control, which must include at least two RGB light sources, reading light intensity sensor values, and motion sensor values. And finally, developing a GUI for easy control of the entire system and to provide light health statuses for our each individual fixtures.
Here we can see the overview diagram, which consists of the hardware architecture and the software architecture. For the FPGA, we went with the Altera 5GX from Intel. This is because it has an HDMI, which allows us to output the graphical user interface, or GUI, to a monitor, has a soft processor which allows for flexibility as compared to a hard processor, and can support an Arduino Uno R3 for us to attach an Ethernet port to. We prefer to use an Arduino over an Ethernet module directly attached to the FPGA because we can use the libraries already built into the Arduino to transmit the data. The FPGA is also connected to a mouse and keyboard for us to control the lights from the GUI. The FPGA transmits the data from Arduino number 1, which then transmits the data to the network through an Ethernet shield, where Arduino number 2 receives the data and outputs it to the DMX fixture through a DMX shield. Arduino number 2 is also connected to a light sensor, which checks the light intensity of the bulb, and motion sensor, which detects motion to turn on the lights. The FPGA also runs code which can turn on a circadian rhythm module, which turns lights on or off based on the circadian rhythm sleeping cycle, and a motion sensing module which turns lights on based on motion. Here's a concept render which shows the microcontrollers and the FPGA with the light fixtures together. And here is a render with the enclosure with the monitor and keyboard and mouse setup.
Our test plan has been set up to test each design objective with two different methods. One will be hardware verification, and the second will be simulating our software. If we look at the first objective, we can see that we're trying to make sure that there's communication with the lighting network system over Ethernet. Now, we can start to test this by looking at our FPGA and Arduino and make sure that the FPGA is in fact sending DMX data packets to the Arduino itself. This requires setting up the Arduino within a circuit and digitally reading what the inputs are that it's getting. The second objective that we'll be testing will be to make sure that we can control two of the RGB light sources. Now we need to make sure that these light sources can receive data inputs and also respond with the correct outputs. We will be using the ModelSim program to test these simulations. Within ModelSim, we will be setting up our own test benches. This will be easy for us to test a range of inputs and also see how these inputs will react and what outputs we should be getting. These simulation tests are very important as they help us to gain an understanding of what the system should be outputting and what we should be looking for when we head into hardware implementation. As you can see in the below example, we took a small screenshot of what a model sim waveform simulation actually looks like. As you can tell, we can create our own inputs and also have our own output signals and look at them and see when each output signal responds to a certain individual input signal. For example, we can see at the very bottom that the red output signal is high for most of the time until the very end when there's the input change. The third objective that we'll be testing is to make sure that our light and motion sensors can transmit data over the network bus. We will first be verifying that the actual light sensors and motion sensors do in fact work. This is easy to do as we can set up these sensors within a small circuit. For the light sensor, we can provide a light input and then read with the multimeter the current outputs or the voltage outputs. The next step will be to verify that the Arduino and light sensor can communicate with each other. We will do this by hooking up our Arduino to our computer and then connecting the Arduino to our light sensor. After that, we will provide inputs to the light sensor and make sure that we're getting the proper outputs from our light sensor.
Hello everyone, this is Yash from Team Mamba Mentality, and I'll be discussing our budget. From our last budget reporting, our budget has changed a little bit. With the initial launch, the plan was to purchase an FPGA board, but we haven't done so yet. The plan was to do this sometime after the spring break, but since schools went from at home or online, we haven't been able to meet face to face yet. So a lot of purchasing will take place either over the summer, most likely before the fall semester starts. From what we accounted for, we have more than enough allotted to us so we can make all the purchases necessary. The changes that have taken place are mainly the Arduino Ethernet shields, DMX shield, and an Arduino board that we'll need to purchase. There have been some changes in the design. We made these changes from a reliability perspective and also to look for scalability or improvements in the future. We do plan on making some improvements in the fall semester, which will go above and beyond what the deliverables are. So all the purchases sometime around summertime is when they'll be made, and again, the funding is enough for what we need. Hello everyone, I'll be discussing timeline. This is Yash from Team Mamba Mentality. Ever since we reported our timeline the last time, which was back in March, it has changed. It had to be adjusted to accommodate for the at-home environment where we're only meeting virtually. There are no face-to-face meetings. There also needs to be additional time allotted to almost all tasks. We have had to halt testing because we need a few equipment from the lab, which we cannot get to at the time. The schedule was also updated to a lot more time for the virtual showcase event and the midterm report. We have gotten enough time to work on all of those things. Thanks to NASA's, TSGC, they've given us an extension, so all those things are falling in place. We are, as we speak, designing the poster for our virtual showcase. It's almost about done. The showcase we'll mostly be using concepts and designs. In visual aids, we have a 3D rendering of what our design might look like, including all the different components like the Arduino board, the FPGA board, the light sensors, and whatnot. Majority of all the components will be purchased over the summer, but for the most part, we've been on schedule to submit our reports on time to the school and to NASA. And the rest of the testing will be done in fall semester once hopefully the schools go back to in person.